I introduced polar bonds in the last video. Now it's time to talk about polar and nonpolar molecules. A molecule is said to be nonpolar if it fits into two categories. The first case is when it contains no polar bonds. Here are some examples of nonpolar molecules that contain no polar bonds. A molecule could be nonpolar even if it has polar bonds, if those bonds are arranged so that they cancel each other out. Carbon dioxide has two polar bonds. The difference in electronegativity between carbon and oxygen is 1, making a bond between them polar. But one oxygen pulls electron density away in this direction, and the other pulls it in the opposite direction. The two dipoles cancel each other out. Another nonpolar molecule with polar bonds is carbon tetrachloride. It contains 4 polar bonds, but when they combine, they cancel each other out. If you've ever done math with vectors, you might remember that when they are added, they result in a new vector, or they result in nothing at all. These 4 vectors add up to nothing. If you have trouble visualizing whether a molecule is polar or not, you could just look at the centers of charge. In CO2, the carbon has a partial positive charge, and the oxygens have a partial negative charge. The center of negative charge, if we average out where these two are, is going to be right here on the carbon, and the center of positive charge is right there on the carbon. The center of negative charge is in the same spot as the center of positive charge. There's no separation of charge, and this means that the molecule is non-polar. In carbon tetrachloride, the chlorine atoms all have a partial positive or partial negative charge, and the carbon has a partial positive charge. If you try and average these all out in space, they average out to be right here on top of the carbon. And that's where the center of positive charge is. There is no separation of charge. So what conditions are needed in order for a molecule to be polar? Well, if there's only one polar bond, the molecule will be polar. There is nothing to cancel out the dipole. Also, if a molecule has more than one polar bond, and those dipoles do not cancel each other out, then the molecule can be polar. An example of a polar molecule is water. The oxygen-hydrogen bonds are polar, and with the oxygen having a partial negative charge and the hydrogens having a partial positive charge. The center of negative charge is on the oxygen. It's the only one with a partial negative charge. The center of positive charge is right here between the two hydrogens. So we have our positive charge here, our negative charge here, and that results in a net dipole. So water is a polar molecule because its dipoles do not cancel. Another example of a polar molecule is ammonia. Now, ammonia is a pyramidal molecule, meaning that the nitrogen sits above the hydrogens and there's a lone pair on top. So you can see here that nitrogen compared to hydrogen is more negative, so it has a partial negative charge on the nitrogen. The hydrogens have a partial positive charge. And so the center of positive charge is below the nitrogen, and the center of negative charge is on the nitrogen, so there is a net dipole. Yet another example of a polar molecule is it's a fluoromethane. So we have 1 fluorine and 3 hydrogens. The carbon-hydrogen bond is not polar. Only the carbon-fluorine bond is polar, and so there's nothing to cancel that out. So this is a tetrahedral molecule, and it's still not. It's still polar, but that's only because it has. It's an asymmetrical tetrahedron. In summary, A molecule with no polar bonds is always nonpolar. A molecule with only one polar bond is always polar. Where people get into trouble is these next two rules. A molecule with symmetrically arranged polar bonds is nonpolar. And by symmetrical arrangements, if all of the atoms are the same, the outside atoms are the same, then tetrahedral, trigonal planar, or linear molecular geometries are rarely, if ever, polar. A molecule with asymmetrically arranged polar bonds is polar, and this is usually involves trigonal pyramidal and bent geometries. Now, so if you have trigonal pyramidal geometry or bent geometry, unless there are no polar bonds, it's definitely going to be a polar molecule.